All right. Okay. Okay. Hi, everyone. Welcome to the Scalable Machine Learning session. So let's see, let me get my, all right. So my name is Mai Nguyen, and I will be co-teaching this session with Paul Rodriguez. Paul, you there? You want to say hi? Okay, you'll see him later. All right. So here's the agenda. So we're going to start out with a kind of a overview of machine learning. It's going to be pretty high level, pretty quickly, but I just wanted to make sure, you know, we are all on the same page with the terms and the main concepts that we'll be covering. And then Paul will be talking about how to scale up R on HPC. And then we'll follow with a break. And then after the break, I'll talk about Spark, which is a distributed computing platform. We'll do some hands-on using Spark, and then we'll hopefully have a wrap up at the end. Okay, so let's get started with machine learning overview. So first of all, what is machine learning, right? If you Google machine learning, you're going to get lots and lots of hits, lots of different definitions. I selected these three here because I think they capture the essence of machine learning. So let's go over these. So Wikipedia defines machine learning as a subfield of computer science that explores the study and construction of algorithms that can learn from and make predictions on data. What is defines machine learning as a type of artificial intelligence that provides computers with the ability to learn without being explicitly programmed. And SAS, which is a analytical software company, defines machine learning as a method of data analysis that automates analytical model building and allows computers to find hidden insights to produce predictions that can guide better decisions and smart actions. Right, so if you take these definitions and you kind of you know, extract out the main parts of these definitions and others like them, I think you'll get you'll get these main key phrases or concepts. Right, so machine learning is learning from data, no explicit programming, discover hidden patterns, and to use for data-driven decisions. Right, so the last two I think are pretty self-explanatory. Right, you use machine learning models to discover hidden patterns in the data in order to drive data-driven decisions. Let's talk a little bit about the first two. What does learning from data with no explicit programming mean? So what this means is that a machine learning model can detect and learn patterns and trends from the data in order to perform a particular task without being given explicit step-by-step instructions on how to perform that task. Right, so for example, a machine learning model can learn how to recognize an image of a cat by processing lots and lots of images of cats, and also negative images of, you know, non-cats, or things that are not cats. So the model is not explicitly programmed to look for, you know, two eyes and pointy ears and whiskers and fur and a tail and four paws. Instead, the model learns what features are important in determining whether an image contains a cat from the positive and negative images and positive and negative examples that it has been given. Right, so that's kind of an important component of machine learning. All right, so from that, we get our working definition of machine learning. The field of machine learning focuses on the study and construction of computer systems that can learn from data without being explicitly programmed. Machine learning algorithms and techniques are used to build models to discover hidden patterns and trends in the data, allowing for data-driven decisions to be made. Okay, so that's our working definition of machine learning. Another kind of important characteristic of machine learning is it's very interdisciplinary, right? So it combines concepts and methods from lots of different disciplines, and currently it's being used in a lot of different fields. So that's kind of an important part of machine learning, and I think that's what makes it so interesting, at least to me. All right, so what are some applications where machine learning is being used? So something that I think we have all been exposed to is recommendations, right? So if you order anything on Amazon or any online, you know, website, you'll often see kind of a list of things that you might be interested in based on your browsing history or your purchasing history. So behind the scenes, there's the machine learning model that analyzes what you have looked at, what you have purchased, your likes and dislikes of customers like you, so that it can provide you this list of things that you might be interested in spending more money on. Speech recognition, right? So Siri, Google, Alexa, behind the scenes, it's processing the sounds that are coming out of your mouth, trying to understand, putting all these things into words, trying to understand what it is that you're asking, and then coming up with an appropriate answer. Right? And then other things like sentiment analysis, face recognition. So these are very common, kind of everyday applications that that we come across that have machine learning behind the scenes. All right, so machine learning approaches. So these are the main approaches. There are others, but these are the main ones. So classification, regression, cluster analysis. So for classification, the goal is to predict a category given the input data, right? So the target is a categorical variable. All right, so what, as shown in this picture here, if you give a machine learning model weather-related variables like, temperature, air pressure, humidity, cloudiness, things like that, the goal of the machine learning model is to predict the category of the weather, right? Is it going to be sunny, cloudy, windy, or rainy? Other examples are listed here, right? Classify tumor as benign or malignant, determine if the credit card transaction is legitimate or fraudulent. So that's another very commonly used application where machine learning is used, and identify the type of customer. These are all classification examples. For regression, the goal is to predict a numeric value given the input data. So the target is a numerical variable. Some examples are listed here: predicting the price of a stock, estimate the demand of a product like, like umbrellas or, skis, depending on where you live and based on the time of the year. Determine the risk of a loan application, or predict the amount of rain. So if the task is to predict whether or not it will rain, that will be a classification problem. But if you are predicting the amount of rain, then that is a regression problem, right? Okay. All right. And then cluster analysis is also another approach to machine learning. So the goal of cluster analysis is to organize similar items into groups. A common example is to group your customer types into different groups so that you can more effectively provide targeted ads. Another example is identify areas of similar topography. So if you're looking at a satellite image, you want to know, where the grass is versus homes versus water areas. You can use cluster analysis to do that. Other examples are to categorize different types of tissues from a medical image or discover crime hotspots. Okay, and then machine learning approaches can be categorized as supervised or unsupervised. So in a supervised approach, the target is known, right? So what you're trying to predict or what the model is trying to predict is known and it's provided. So you have labeled data. So classification and regression approaches are supervised. Unsupervised approaches, on the other hand, the target is either not known or not available. So your data is unlabeled. So cluster analysis is unsupervised. All right, so you can think of a machine learning model as a mathematical model with parameters that maps input to output. And these model parameters are adjusted during model training in order to change that input to output mapping. And so these parameters are learned or estimated from the data, right? So this is why machine learning is data-driven. And the goal in estimating or in adjusting these parameters is to minimize some error functions so that the model outputs what it should output, what you would like it to output. And so in general, when you construct a model, there are two phases. There's a training phase where you adjust the model parameters based on the data. And then once the model has been trained, the parameters are frozen, and then you can apply that trained model to new data. And that is done during testing phase. So testing a model on new data is referred to as inference. And the goal is you want your model to perform well, not only on the training data, but also on new data that was not used during training. So you want the model to generalize well to unseen data. Okay, so real quickly, so what is scalable machine learning? So kind of in a nutshell, it's applying machine learning to what's referred to as big data. So then that begs the question, what is big data? So big data can be characterized by these things that people call the V's of big data, right? So the V's of big data are things that characterize data that is considered to be big data, and also describe the challenges of big data. So, you know, there are lots and lots of V's. People have been really creative with these V's, but these are the main V's of big data. So first and foremost, there's volume, right? You're dealing with a huge amount of data. There's velocity, which means that, you know, the speed at which data is being generated, and also the fact that data is being generated continuously. So as the data comes in, you have to process it and analyze it. Variety has to do with the different forms of data, right? So you're not dealing with just numeric, you're dealing with text and images, geospatial, voice, you know, lots of different types of data. And then veracity is the quality of data, which can vary greatly depending on, you know, the data source, how it was collected, and things like that. There's also a fifth V of big data, and that's value, right? So the goal of processing big data is to extract value from data. So it's not sufficient to just collect all this data. You have to process it, you have to analyze it in order to gain some insights that will help you in your decision-making process. Okay, so then extracting value is at the heart of analyzing any data, right? Big, medium, or small. And this can be done using machine learning techniques. With big data, you need new technologies and approaches in order to address these challenges of big data, the V's of big data. So parallel processing, scalable algorithms, distributed platforms, these are new tools that are needed to address the challenges of big data. And we'll cover some of those things, introduce you to some of those tools and techniques in this session. Okay, questions, comments? Okay, so then I will hand it over to Paul.
Okay, I'm sharing my screen now. Hopefully you guys can hear me. And
yes.
you see my screen.
Maya, do you hear Paul very well? Paul, I'm not hearing you very well.
How about now? I just moved my microphone.
It's a little bit better.
It's a little bit better, but not tremendously better. All right, is this a little bit better?
I think that'll do.
Okay. Okay. So in this session, I'm going to talk about R and scalable machine learning, and really, it's R is sort of an example. It's, you know, there's other packages I'll make some references to, like MATLAB and Python, and talk about R in the context of HPC and scaling. So you don't have to, you know, even if you're not interested in R, I think the scaling questions is hopefully generic to everything. So the outline for the talk will be R and scaling, talk about parallel R and embarrassingly parallel R, and kind of a little bit of a case study or exploration of R with some big data. So if you haven't used R, this is what a typical workflow looks like. There's an integrated development environment called RStudio. It runs on Expanse through the Expanse portal. So we have you know, you access it through a browser. Like a lot of development environments, it has, you know, some integration of your script that you're editing and some outputs. And I'm not going to go into details of that, but we'll see a quick example. Your typical R code workflow looks like a lot of other kinds of workflows. You're reading data, you're processing data, and then running models. So the strengths of R for HPC, in my, you know, from what I've seen, data wrangling, R has some pretty good tools for managing your data, manipulating data, transforming your data. Python has become pretty good. Python pandas is pretty good. I think, so, you know, it comes down to maybe your preferences more than anything. There are some statistical procedures implemented in R that you probably won't find in things like Python or even MATLAB. Certain kinds of things I've come across from doing projects on HPC and supporting people are things like imputation methods, sampling methods, certain kinds of regression stuff. Certain things was always, I think, the best, but then other people have packages that are specialized and perhaps better. So the Monte Carlo Markov chain Monte Carlo methods. There is a package called Stan that is produced by the people who did WinBugs a long time ago and some of the top some experts in the field, and it has a lot of good bells and whistles, and we have that running on Expanse. Some machine learning models I think have pretty good R implementations that I kind of like. So something like the random forest is pretty good. So in a nutshell, when you're scaling R, there's different things that you might come across that you need. So if you're scaling big matrix operations, well, R is compiled with the BLAST linear algebra pack. So, if you vectorize your operations, you're operating on a matrix at a time. For example, you'll get good speed up, and it's very, very similar to MATLAB and Python that way. R packages there are R packages that help you support out-of-core multi-node or distributed data processing. And same for MATLAB and Python. So whether you use one or the other, I mean, nowadays I think a lot of these tools have very similar keys. And we'll talk a little bit more about some of that. And as I said, some of the machine learning implementations, on R, maybe they're a little bit better. Maybe they've worked in the parallel backend. So depending on the model you run, you might have to review what the available options are. And so, for example, when you log into R, and I'll show examples of how we log in later, but there is a command called session info, and it'll talk about how R was compiled. And you'll see on Expanse it was compiled with BLAST and LAPACK. So let's think a little bit about what happens when we start doing bigger computation. So I'm showing you an example of a linear model, and algebraically, you can find the solution by taking the inverse of x and multiplying it on each side of the equation. So there's a procedure you use that's well known in matrix algebra. You could also take derivatives, or better, you could use something like QR decomposition. And so if we look at, just for comparison, we can look at the different options with R on one compute node, and on the x-axis I have data matrix size, and the y-axis I have wall time. And for something like solving linear systems, the decomposition methods are very fast. They grow, they don't grow as fast. They don't grow as fast as these other methods. So as your data matrix gets bigger, they don't grow as fast as taking inverses, for example. And inverses don't grow as fast as doing gradient descent, for example. So that's the kind of thing you want to keep in mind when you start scaling these kinds of certain kinds of computations. So how do we implement something in parallel? So R has a package called do parallel. It provides the back end of something called for each, which is a parallel processing command. It uses threads across CPU cores to pass data and commands. And it also works on top of a multi-node execution. And in that case, it's going to run on top of MPI. So let's see what this looks like. So here's my R code. I may have to install the package called do parallel. There's a library command. So these are standard R commands to install a package and load the package. And what's different here is you have to do a register to register the cores that you're going to use. So in this example, I'm registering 24 cores. And then presumably you're going to have some data, and it's going to be in some data frame, and you're going to want to process it in parallel in some fashion. And to do that, you're going to have a for each loop. The for each loop is going to have an index, just like a regular loop. It's going to have some way to combine the results. You can kind of change. You have some options on changing how things get combined. It usually gets returned as a list. There's a do par command that goes along with the for each. It tells it, if you say do par, it's going to run across cores. If you just say do, it'll run serially. So you can easily run comparisons between a serial and parallel execution. And then you have your code and you return some result. And the thing to keep in mind is, you have to do this when you set up this kind of problem, this kind of computation. The for each is going to copy data to every core. So it has to figure out what has to be available for the commands inside the loop. And so the memory management really becomes your main issue. Parallelizing is pretty straightforward, but making something work well depends more on the combination of how independent your code is between different indexes and how much memory you have to move around. There's also an option in R to do multi-node. It's very similar to what we just saw, except you are allocating a cluster as a parallel backend. And the commands are basically the same. Oops, sorry about that. The commands are basically the same. There's a do par, except now you have to worry more about memory management, because instead of just copying data across cores, you might have to copy data across nodes. So if you're copying data across nodes and maybe you have, some more interaction, it may not be efficient. All right, so I have a short demo I'm going to do, and what I want to show you is I'm going to log into the portal. Actually, I've already logged into the portal. I got our studio session going. And then I'm going to log into Expanse and use the top command to look at the performance of this little R function I have. So in the slides, I have the steps that I'm going to go through, and I'm just going to go ahead and go through that. Let's see, I wanted to preview it really quick. So I'm going to open up a script. The script, I've already installed the do parallel package on this particular training account. And then I'm going to log into an Expanse shell and log into the compute node that's running the R script. All right, so let me switch screens and show you what this looks like. Okay, so I've logged into, remember I went into the Expanse portal. I think you guys have probably seen this. I started an interactive app for RStudio. In this case, I selected one compute node with 64 cores. That's our RStudio standard, our limit. And I have this application that's just going to run. It's just going to, I installed do parallel. And it's just going to run. Let me see if I can scroll through this a little slower. I've got 32 cores, so I'm using about half the cores. I set up a random matrix. I just create some data, some target values with some coefficients. And then I'm just going to do something like a bootstrap sampling. I'm just going to split the data according to some, sample of the indexes, and run the linear model. And I'm going to show you how you can see what kind of memory sizes you're using in R. I'm just going to sleep for 30 seconds so I have time to go into Expanse. All right, so I'm going to run this. So it's running, and you're going to get a message about how big the X data matrix is. And I've logged into Expanse. I can see what the job is and where it's running, and I can just SSH into that. I can do a top -u. I'm using some training account. I'll just put $user, and so you can see I have the R session running. And if I hit a small f, it shows me other fields. I can ask top to show me. I'm going to have it show me the last used CPU. I had escape to go back. And now I see I have a bunch of R threads running. Oops. Okay, it looked like it finished. A bunch of R threads were running, and wherever it runs, it was showing me the CPU that it was running on. Let me go back real quick to this RStudio session. Okay, I think it's in the wait stage now. All right, so again, I've logged into that compute node. I'm looking at all the things that are running here. The The RStudio is one of these threads, or we're sitting on, or rather, it's sitting on one of these cores. Okay, the whole thing, I'm going to run it again. And then we see our parallel. Remember, this is I asked for what, 32 cores, so I should see 32 R session commands, and they're all running on different cores. So this is the kind of thing you want to do as you run. Oh, by the way, one more thing. As you run, you can look and see how it's running in parallel, make sure it's using different cores, and you can look at the total memory usage. In this case, I'm not using that much memory, only 33 gig, I guess, out of 200 something gig total. And I can tell you from experience that, even though my X matrix isn't that big, it's only 152 megabytes, there's a lot of overhead when you're running something in parallel. And so that's the kind of thing you want to do when you're running something like this in parallel, when you're using this for each command. Get a sense of how things start out with maybe a relatively small size data set or data frame, whatever you're processing, and grow it. Get a sense of what the overhead is. So there's some overhead in here. And if I can tell you, if I run probably 100 times bigger, or maybe 10 times bigger, it's going to slow down a lot. And at some point you'll crash this interface if it runs out of memory. Okay, so that was a quick demo. It uses some of the things, if you remember from, for those of you who were here earlier in the week, Mahi talked about these kinds of commands to monitor your performance. Okay, let me go back to slides and maximize my screen. Okay. So parallelizing for loops. So just let me summarize real quick. So with R, and there's a do parallel command, you make a cluster, register a cluster, you have this for each, you combine results. MATLAB and Python are pretty similar. So with MATLAB, you define a cluster. You have a par for. You have two ways to do parallel loops, something called a par for, just like a for each. But you have another way to create distributed arrays. So it's a little bit more flexible in that manner, in that you can control how data is distributed in your array. And then you have this way to gather data from an array. But it's a lot like R. I can't tell you off the top of my head if it's like better than R, but it has a little bit more flexibility. MATLAB is built around matrix objects. Python is very similar also. You are setting up some modules this is Python with Dask in particular. So you're defining some clients. Now with Dask, if you were in the talk earlier, I think that was the other session in the main room, you can parallelize a for loop. You use something that's delaying the actual function execution, and then you have to combine the results. And then you have to explicitly say, okay, now compute the results. And that's when it actually gets parallelized and computed. So Python has a little bit differently, but the steps are kind of the same. Okay, here's another way to think about scaling. What if you have this, and I've come across this in a lot of cases, and people find this kind of useful. So, you're doing something on a laptop, you just have a lot of data, suddenly you need to go to an HPC system. This situation comes up. But you can easily split your data up into n parts. If you have that kind of situation, then you can maybe do something we call embarrassingly parallel, which is in your situation, you really just need to process a bunch of instances of R, and each instance should be processing one part of this data set. So in this case, you can have a Slurm batch script that uses npi run command, and you want to wrap that around a little script. In this case, I'm using an example of a Perl script. The Perl script is just going to figure out which is the rank, which core you're running, or which MPI task you're using, pass it to R, and then R can just do its thing. So I've come across very many situations where it's been easy to do this for some statistical or analytic processing in R. And the key thing here is that these two programs together, your R script and your Perl script, That's what gets distributed across nodes by Slurm and your MPI parameters. So for example, your Slurm script would look something like this. I'm not going to go through all the details. It's kind of a standard Slurm script. You would mention that you have 2 nodes and you have a number of tasks per node. So your number of tasks is your MPI ranks. So in this case, I'm going to have 256 MPI ranks. That means I'm going to have 256 Perl R instances running on 1 core each. Okay. And it's going to look visually, it's going to look something like this. And the main thing you have to keep in mind when you have a bunch of instances processing your data set that it's been broken apart, you're going to want to have some final script that combines your outputs. Okay, so that's one way to put 1 R instance on each core. The other, excuse me, another way to do this is to have just one R instance on each node. In this case, my task per node is 1, so I'm going to have 2 MPI ranks. I'm going to have 2 R script, Perl R script instances, and now each one can use a do parallel. So pictorially, visually, it might look something like this. There's your instances. They each have access to all 128 cores on a node. And then again, oops, I'm sorry. And then you're going to have some final way to combine it. So this is, again, depending on your situation, this could, these kinds of things could be very useful. All right, so that's scaling. Let's think about, oh, okay, I'm sorry, I went backwards. All right, so let's think about the case where, okay, I have a big data problem and there's some package I want to use and I need to, I'm hoping that the package has implemented some parallel backend. So this is someone recently asked, gee, how would we run a lasso on a very large data set? And they weren't specifically asking about R, but I did a kind of an exploration. R has a big lasso package when you have a case where the data set is too big for RAM, so the out of core kind of situation. So I created a CSV file that represented the data matrix and some outcomes. I just produced it, with random data. So my X matrix here was 100,000 rows by 50,000 columns. I'm going to explore how R does it, MATLAB and Dask and Spark and Keras. But the thing you have to remember, so this isn't a direct comparison. Lasso implementations can differ. So here's Lasso has been around for a while. It's a standard tool in the machine learning toolbox. You got to be aware of that. You also want to, if you're going to do something like this, make sure your X, Y, and your betas are kind of nice. They shouldn't be super large. You don't want to have precision. Just to remind you, or give you a sense of what lasso regression is all about. Lasso is basically linear regression plus a penalty. So people think of it as a penalized loss function. So in linear regression, we're minimizing the mean squared error. Here, you're minimizing the mean squared error plus some penalty on the size of your coefficients. But when you're using a penalty, that's the same as using a constraint on your problem. So it's really a constrained optimization problem. Different implementations of Lasso could take to either approach. Okay, I won't say much more about that, but we're going to see that R actually takes an approach more like the constrained optimization. Other packages are doing more like a penalized loss function. Okay, so that means you're going to have different fit methods. Maybe you're using coordinate descent. Maybe you're using something from the regression world, which is called stepwise. Different implementation could be, parallelizing different ways, splitting up data, maybe the computations, for example. There is some questions about, how are you going to load your data and read the data efficiently? So different packages will have different ways to support that. In some sense, that shouldn't be the big burden, but it's good to be aware. Okay. Okay, so all these packages have special functions. They handle out-of-core data sets. Sometimes I find it was better to have the X and Y together in one data set. Sometimes it's better to have two data sets. These were all run on Expanse as batch jobs, so not through a notebook or portal. And they're all set up to run on one compute node and use the scratch space. I didn't test these out on large memory nodes. Presumably, the data I have here is pretty big for one compute node. It's too big. And but we do have large memory nodes where maybe it would run without, having to do some of these things. I mostly use default parameters. I didn't do a lot of optimization, so I don't want to consider this a benchmark study by any means. Okay, hang on just. All right, so R has a big lasso package. It's built on top of a big matrix package. You can find details there. The issue I found was that the file backend for the big data object, you have to, when you load the data, you have to say, put the file backend back, whatever doesn't fit in memory, put it in the file in this location. That was hard to get right. The options weren't quite documented correctly, or something was missing. So I think I had to hard code it. I ended up running out of scratch space as the working directory. Okay, but I was able to get this to work, and it worked in about 2 hours. I got some results. I have the Slurm script and R example in the GitHub repo. So if you want to look at these kinds of example, you can look at that in more detail. Just to quickly show you what the nature of this looked like. There's a package called Big Lasso. You're reading data. And I had to use this, again, I'm reading a big matrix, but for the X matrix, I had to set it up as a file-backed matrix. And that's what these parameters are for. And then you run this Big Lasso command. Normally, you would run, if you're doing Lasso in R, there's a general linear model package that has a Lasso command. And the parameters are all basically the same. Except in this case, it was nice because it gave you an option to tell it how many cores to use. All right, so the batch script looked like this. I'm not going to go through this in detail, but this is how you would run things in batch in R. MATLAB has a function to handle so-called tall tables and read in a large CSV file. Unfortunately, the lasso needs a tall array, so there was a little bit of confusion there. Luckily, I remembered from previous MATLAB use that there's a table to array function. MATLAB I've never liked the way they handle heterogeneous data like a data frame. They have a table thing, and I think now they have something even newer. But I was failing with MATLAB. I was getting disconnection errors after processing. So I didn't fully track down what the issue was with MATLAB. Dask, it has some nice tools. It's a nice way to build your data frame. It's built on top of scikit-learn. There's some options when you're reading big data, like the block size parameter you have to maybe play with. This one, the problem with DaskML, it repeatedly calls the sklearn lasso with a partial fit. So it iterates one at a time. So that's not necessarily a bad thing. But it's not ideal. It's not like a package specially built for a big lasso. And it was probably doing a gradient descent. So it ran for several hours, and it was running, but I don't know how far. I'll tell you how far it got. If you remember back to the slide where I was showing regression problems, remember the stochastic gradient descents just take a lot longer than when you can solve a problem analytically. Spark, Mai's going to talk a lot more about Spark. It does have a machine learning package that has a lasso feature. Again, I think it's based on stochastic gradient descent. And Mai's going to talk more about these options. It was also running for a while. And again, I didn't let it finish, so I'm not quite sure how long it was taking. Keras, Keras is built kind of for big data or to parallelize things really well. With Keras, there's something called a TensorFlow dataset object. that you can use as a data generator to read batches at a time from a file. It's a little bit tricky though to get the shapes right. So what we're going to see tomorrow more with the deep learning is that, Keras has ways of assuming things about your shape and making it flexible. So you just have to get that set up right. I set up basically a 1-layer linear neural network with the penalty regularizer on the weights. So it kind of mimics lasso. It's not really the same as lasso because it's not giving me, all the bells and whistles that you would get on a lasso. But I was able to run this in like an hour and get some results. I didn't set up conversions options. That was the main reason, one of the main things that it doesn't make it look like a lasso. So I don't know. I can't say for sure that I got, the best results, or if maybe I should have let it run for another hour, for example. But that's the kind of thing you would do with Keras. Okay. All right, so here's some notes on what I've been talking about. If you have a big data problem and you want to, your data is already scaled and you need just bigger machine, start with something small. See if you can just get a sense of how things start to scale. The packages I was using in these cases, they all kind of worked as documented, but they always require some particular, implementation issue for your particular example. Maybe there's an environmental option that you have to think about, either, for the session or the job. Okay. All right. Just some final notes. Use R directly on expands. I think Mahi already actually talked about this the other day. The module spider, for example, and loading some of your modules. It would look something like this. If you need to install R packages into your own directories, I was able to install the doParallel package without any problem from a training account through the portal. I find that sometimes you would really rather be on a compute node when you install this, especially if there's like a lot of, maybe it's a big package, maybe it has to do some compiling. Sometimes you have to be explicit in your parameters for install packages, for example. And as Mahi said the other day, when you have certain packages that have a lot of dependencies, maybe they're going to, have certain dependencies that don't fit well on our expand system. There's also the singularity option. So where you have a singularity container that has an R environment. Just a quick note, as your data needs do get bigger, there is an R interface to Spark. And Spark R, I think Maya's going to talk a little bit more about Spark R. I know she's going to mention it. So when you get to the point where data is really big, then maybe, you go to Spark R if it's big and distributed. If it's kind of too big for your laptop, but maybe fits in one compute node, maybe you don't need Spark R. R does have an interface to Keras, if that is the kind of thing you want to do. There are a couple other packages in R, which I have not used in a big way, so I can't speak for it. But in principle, you can do things with GPU. There's this package to help you with certain kinds of big matrices that maybe in some cases might work better than Spark. Okay. So I think I have a couple more minutes. So are there any questions? Anything you want to go over, talk about it more? I see there's let's see.
We don't have anything in the chat, but feel free to unmute, folks.
Yeah. So just to I'm gonna just make a couple final notes. So in the GitHub repo, I have the examples if you want to do an embarrassing parallel R. And remember, if you want to do something embarrassing parallel R, the same example could be used if you wanted to do it instead with Python. or anything, any particular program. It's just a matter of wrapping your computation inside of something that gets the MPI rank and using that rank to specialize or indicate to your program which part of the data, which part of your problem to work on. So that's in the GitHub, and as well as the big lasso example from R is also in the GitHub, and also this short for each example is also in the GitHub. So if you want to run that at some point, you can just yeah. I think that would be my final thing to add.
Okay, welcome back from break, everyone. So we're going to be talking about Spark now. So here are the topics. We'll start with the history of Spark and then talk about some of the main concepts of Spark. Then we'll do a couple of hands-on to kind of get you, introduce you to Spark, and then we'll talk a little bit about R on Spark. All right, so let's start with Spark. So Spark is a computing platform for distributed computing. So it was designed to run on, to process big data workloads. So it has built-in parallelism and fault tolerance, and it can run on commodity clusters. So what that means is that it can run on, a cluster of systems that are networked together using commodity hardware, just regular hardware that you can get off the shelf. So you don't need a supercomputer like Expanse to run Spark on, although you can run Spark on Expanse, which is what we're going to be doing with the hands-on. But you don't need a supercomputer. You can just run it on regular hardware. Spark provides interactive querying, iterative analytics, streaming processing, along with batch processing. And the design goals for Spark are to provide speed and computation, ease of use, generality, and a unified platform. And we'll talk about each one of those as we go along here. Okay, so Spark began as a research project at the AMP lab at UC Berkeley. And they published a paper in 2010, and then in 2013, they contributed Spark to the Apache Software Foundation, and that's the world's largest open source software foundation. So it is open source, which is one of the appeals of Spark. But there are also commercial versions, most notably provided by Databricks, and Databricks was founded by many of the people that started Spark at UC Berkeley. All right, so since Spark was designed for big data workloads, processing speed is essential. So Spark provides speed by making use of in-memory processing. So it tries to store data in memory as much as possible. And in particular, when you have a distributed system, it exploits this distributed memory that is available in all of the system across your, in your cluster in order to cache data. And intermediate results are written to memory whenever possible. You can also spill to disk, but whenever it's possible, Spark will use memory to speed things up. Okay, so how does Spark manage data in a distributed system? It does this using what is known as resilient distributed data sets, or RDDs for short. So a central concept in Spark is the abstraction of a large data set as a distributed collection of objects, right? And so this data abstraction in Spark is provided using RDDs. So it's essentially a programming construct for storing data. So Spark uses RDDs to partition the data, to distribute the data across the nodes in your cluster. Okay, so an RDD, let's talk about what an RDD is. So first and foremost, it's a data set, right? It's a way to store a collection of data. You can create an RDD from ingesting files from your local file system. You can also read it from an external data storage like HDFS or a relational database. You can also create an RDD from an existing RDD, and we'll talk more about that. An RDD is also distributed, right? So data is divided into partitions, and then these partitions are distributed across the systems in your cluster. And then RDD is also resilient, and that means it has fault tolerance. So when you're talking about, you know, a cluster of machines, there could be many points of failure. And so when something fails, you don't want to have to start all the way from scratch in order to, you know, process your entire data set. And this is especially important when you're talking about a very large data set. So fault tolerance is very important for when you're processing large data sets. And Spark provides fault tolerance by keeping track of the history of operations that have been performed on each data partition. So if something happens, you know, a node fails or a core fails, and you have to figure out what went wrong with that partition, you can look at the history of operations that have been performed on that data partition in order to regenerate it. Okay, and all of these, you know, all of this functionality is provided automatically by the Spark engine through RDDs. Okay, so when you write a Spark program, the first thing that you need to do is create a Spark context object, right? An object of the Spark context class. So this provides a way to create RDDs, and it provides you, you know, all the functionality, you know, the fault tolerance, the data partitioning, the data distribution that is provided by the Spark engine. So this code snippet here tells you how to do that. So you can first create a Spark conf or Spark config object, and you can specify the, you know, your configuration parameters for this Spark application. And there are many configuration parameters in Spark. So for example, here you're specifying the application name. You can also specify things like, you know, the URL of the master node, how much memory to use, and things like that. Then you can pass this config file, the config object, into a Spark context object, right? And so then you use the Spark context object then to create RDDs. So there's several ways to create RDDs. You can read data from files in your local file system. You can read data from an external data source like HDFS or a relational database. In this case here, this example here shows how to read from HDFS. You can generate data. So this is generating a list of numbers, and this is specifying that you want this RDD to be partitioned into 3 partitions. So you're explicitly telling Spark to divide this into 3 partitions. You can also create an RDD by transforming an existing RDD. So in this case, this is an existing RDD, lines. Then you're applying a transformation or an operation called filter. So you're filtering all the sentences that start with Spark, and then that will create a new RDD, new lines. Okay, so then RDDs can be processed using 2 different types of operations. You have transformations and you have actions. So a transformation is an operation that you define on an RDD. And when you apply a transformation to an RDD, a new RDD is created to hold the changes of that original RDD. An action, then when an action is performed on an RDD, that triggers all of the computations that have been defined on that RDD, and then a value is returned. So here's kind of a schematic view of that. So this is your text file. You read it, your data from your text file. That creates an RDD. You apply a transformation that creates another RDD. You know, and then another transformation will create another RDD. And then when you apply an action to that RDD, all of these transformations are then executed, and then the results are returned. So an important thing to note about RDDs is that they are immutable. That means the contents of an RDD cannot be changed. When you want to change an RDD, right? So when you want to filter an RDD, then another RDD is created in order to hold the changed data, okay? Another important thing to note about RDDs is that transformations on RDDs have lazy evaluation, right? So the operations that you define on an RDD are not immediately processed. Instead, what happens behind the scenes is that the Spark engine will build a plan of operations, right? So it has this list of transformations, this list of operations that need to be applied to this RDD. It doesn't process each one as soon as it's applied, but instead it builds a plan of operations. And these operations are executed only when an action is performed on that RDD. So in other words, actions will force the computations that have been applied to that RDD. So Spark does this so that it can optimize, all of the different, the series of operations that have been defined on that RDD. So it allows for optimizations in generating the actual plan for implementing those operations. So for example, again, this is the kind of similar example that we saw. So this is an RDD. We're applying an operation, a filter operation on it to get a new RDD. Nothing actually is returned here if you type this line of code into Spark. Behind the scenes, this operation is taken into account along with all the other operations that have been defined on this RDD. And then the Spark engine will optimize the sequence of operations on that RDD. And then when an action is called on that RDD, then all of these operations will be executed and then the result is returned. Okay. So we can look at a specific example to show how transformations and actions are used in Spark. So we can look at word count. So word count is kind of like your canonical example for illustrating parallel processing. So it's like your hello world of programming. All right, so word count. Sorry, I just sneezed there. Okay, so word count reads data, right? Reads text data, and then it counts the number of occurrences of each word. So it's just counting the number of times that a word appears in a data set. So it's a very simple problem, but it's an easy way to study parallel processing. All right, so word count can be implemented using two operations, map and reduce. So in this example, what we're seeing is here, this is our input data, right? This is our text data. This data is split into different partitions. And then when you apply a map operation to this, the map operation will generate a key value pair for each word that it sees. So it sees the word deer here. It generates a key value pair where the key is that word and then the value is 1 to specify that this is an occurrence of that word, right? So it does the same thing with bear and river and so on. The map operation then is then followed by a shuffling operation where the pairs with the same key is moved to the same partition. So bear is moved to here, and this bear here is also moved to the same partition. This is so that when you apply a reduce operation, these values with the same key then will be summed together, right? So that's what happens in the reduce operation. And then at the end, you just collect all of the different results together. Okay, so this is what it looks like when you implement word count using RDDs and Spark. So this is your text file that you've read in. You apply a flat map, which splits the text into words using white space. And then you apply the map operation, which creates the key value pairs. And then that's followed by a reduce operation, which creates, which sums up the counts. And then this is the action that will return the results. And this is the code that goes along with this, right? So this is reading in the text file that creates the RDD. Apply a flat map, which splits the data into words. Apply the map operation, which creates these key value pairs. And then apply a reduce operation, which sums up the values of the same key. And then that's followed by an action that returns the results. Okay. All right. So we've been talking about RDDs, and RDDs is a very important concept in Spark. But later versions of Spark use higher level abstractions to RDDs, and they're called data frames and data sets. So they're higher level of abstractions. They provide improved performance, better scalability, and because they're higher level, they're easier to use than RDDs. But underneath the covers, data frames and data sets are made up of RDDs. So you can convert a data frame to an RDD and vice versa. And you can also use data frames along with RDDs, and similarly with data sets. So what is the difference between data frames and data sets? So because they're both made up from RDDs, they both have lazy evaluation. They both are immutable. They both are organized as a collection of rows. The main difference is that a data set has static type checking. So you would use data sets in strongly typed languages like Java and Scala. And data frame does not have static type checking. So you can use data frame with languages like Python and R. And so we are going to be using PySpark, which is a Python API that is provided in Spark. So we're going to be talking just about data frame. We're not going to work with data set in this session. Okay, so using data frames then. So now, when you write Spark code now, you're going to be using either data frames or data set. When you write a Spark application, you write a Spark program, again, the first thing that you need to do is create a Spark session object. So what used to be Spark context in the RDD world is now referred to as Spark session in the data frame world. So again, this allows you to create data frames and allows you to access all the fault tolerance, the data partitioning, the data distribution that is provided by the Spark engine. So very similarly to the way that we created the Spark context in RDD, with the Spark session, you can also define a Spark conf object. You specify the configuration parameters, and then you pass that conf object into a Spark session object, right? And by convention, this variable name is called Spark. I mean, you can really call it anything, right? It's just a variable name, but by convention, this variable name is Spark. Okay, so then similarly, similar to RDDs, there are several ways that you can create a data frame. You can read data from files on your local system. This is reading a CSV file. You can also do read.txt, which is a regular text file. You can read data from an external data store, like HDFS, like a NoSQL data store. So you just preface that with HDFS here. You can generate a data frame. So this is creating rows of employee data, and then you do, you call create data frame to create a data frame from that data. You can also transform another data frame, right? So this is filtering where the column, where the name is Mary, and creating a new data frame. And then similar to RDDs, data frames can be processed using transformations and actions. And again, data frames are immutable, and transformations on data frames have lazy evaluation, again, because that allows for optimizations of the sequence of operations. And then the operations that are defined by the transformations on a data frame are not executed until an action is performed on the data frame, right? In a similar way with RDDs. You can persist data through caching. So that means that you can explicitly say that store this data frame in memory in order to avoid recomputing and speed up processing. You can specify different storage levels. So this data frame.cache here tells Spark to store this data frame in memory. Persist means serialize it and store it in memory, and then you can also unpersist something that remove it from the cache to make room for other data. So this is kind of a general, the structure of a Spark program, the general structure of a Spark program. So again, the first thing that you need to do is create a Spark session. right? So you define a Spark conf object, you pass it through the Spark session object. Then you create your data frame by either reading in from local storage or external storage or creating your own data frame. Then you can apply transformations and perform actions, and you repeatedly do this until, you know, whatever, to process whatever operations that are necessary for your application. And at the very end, you want to stop the Spark session using spark.stop. Okay. So this is kind of the generic and kind of the general structure of a Spark program. Okay, and this is a high level look at the Spark architecture. So there are three main components. There's a driver, there's a cluster manager, and there's the executors. So the driver program is where the Spark application starts. And this is where you start the Spark session. You create the Spark session object. And the driver is responsible for driving the application, right? So it's responsible for maintaining information about the application, responding to the client application, returning results, getting input, planning, coordinating the execution of the program. It also distributes the work to the executors that are running on the worker nodes. And then there's also the cluster manager. So the cluster manager controls the physical resources. So the nodes, the memory, the disk, things like that. So the cluster manager will communicate with the Spark session in order to monitor and allocate resources that the executors need in order to do their processing. The worker nodes are the physical nodes, and the executors run on the worker nodes, right? And the executors are what actually execute the operations that are needed for the application. And so the executors, so the driver program will assign tasks to each executor. The executor will process the data and then return the results back to the driver program. Okay. So another design goal for Spark is to provide ease of use. And it does this in two different ways. So one way is to provide APIs in several different languages. So there are APIs, there's Java, Scala, SQL, Python, and R. So that means that a developer who is familiar with Java can write code to make use of the Spark engine. Or for data scientists who are familiar with Python, you can use PySpark. Or if you're more familiar with R, you can use Spark R in order to write a Spark program. Spark also provides interactive shells in Scala, Python, and R. So this allows you to, if you're familiar with R or Python, you can just, kind of sit down and do an interactive session with the in the R session or with the in Python. So this allows for, kind of quick interactive session, quick debugging, kind of, interactive querying with the Spark engine. So this makes it very easy to use. You can do do things interactively instead of just submit things to a batch processing process. So this gives this is a word count example that is given in different programming languages. So this is PySpark. This is the Python one that we looked at. This is Scala. The middle one is Scala, and this is Java. So you can kind of see, the similarities, right? So the same transformations are done. So you read in the data, right, from HDFS. Then you apply a flat map to split the text up into words. Then you apply a map operation to create the key value pairs. And then that's followed by a reduce operation to sum up the values of the same keys. So you can see, that's done in PySpark, Scala, and in Java. Right, so all these things do the same thing. Okay. So another design goal for Spark is to provide generality. And generality is achieved by providing support for several data sources. So as we've seen before, you can ingest data from your local file system or from HDFS or from a relational database or a NoSQL database like MongoDB, or a distributed streaming platform like Kafka, or from S3 and others as well. So there are many ways that you can ingest data into your Spark application. Spark can also run on different platforms. You can run on Hadoop, you can run on Kubernetes, you can run on the cloud, right? So AWS has Spark installed that you can use. You can run on Expanse, like a supercomputer like Expanse. You can also run Spark standalone on your laptop. So the code that you can run on your laptop will run on AWS or on Expanse, right? It's the setup behind the scenes that changes, but the code itself should run pretty much as is if you're running the same version of Spark. Generality is also provided by Spark by providing support for different types of workloads. So you can do batch processing on Spark, you can do streaming processing with Spark. There's also support for different types of applications like machine learning, SQL, and graph processing, and we'll talk about that next. Okay, any questions so far? Comments? I'll stop here for a little bit just to let people kind of soak that in. Okay, so let's continue on then. So another design goal for Spark is to provide a unified platform for different types of analytical processing workloads. So the idea is that the Spark engines or Spark core provides the core capabilities for distributed processing, right? So the fault tolerance, the data partitioning, the data distribution, all of that is provided by the Spark engine. And then on top of the Spark engine, Spark also provides these high-level libraries to provide functionality for different types of workloads. And we'll talk about these different libraries next. So one of these libraries is Spark SQL. So this provides support for SQL and query processing. So that means that you can, write code using the SQL commands that you're familiar with, right? Filter, select, count, and things like that. And you can do that using, the Spark SQL library is available in SQL, Scala, Java, Python, and R. And regardless of which programming language you use, right? If you use a filter operation in R or in Scala, under the covers, these operations are automatically processed and converted into operations on RDDs by the Spark engine, right? So everything, under the covers is RDDs and operations on RDDs. And so that means that the underlying code that is generated, regardless of what programming language you use, is identical, right? So that's why, even though there's lots of different APIs, everything works the same way underneath. Okay, so here's a couple of examples. So if you know SQL, this should look very familiar, right? So this is selecting the highest count from a table called flight data, and you take the very first, the first row that gets returned. You can do the same thing using PySpark, right? So these two things perform the same operations. But if you're familiar with SQL, this will be very familiar to you. If you're familiar with Python, this should look very familiar to you, okay? And both generate exactly the same operations underneath. You can also integrate SQL queries with Spark commands, right? So this is a SQL query. You can have that as part of a Spark command, right? So you process this query, put the results into a data frame, and then perform, this is just displaying the first 100 rows. And then you can use that as part of your PySpark code. Okay, so that's Spark SQL. the next library is Spark Streaming. So this provides scalable processing for real-time analytics. So the idea is that the way that Spark does streaming processing is it divides the data stream into small parts of data called micro batches of the data. And so the same operations that you can apply to your regular data, you can apply to streaming data. And the Spark Streaming library is available in Scala, Java, and Python. So real-time analytics or near real-time analytics is the analysis and use of data as it enters the system. So some examples are, identifying a fraudulent credit card transaction at the point of sale, right? So when the system receives this transaction, it has to process the data immediately and return the result in real time or near real time, right? They can't store it and process it overnight, right? It has to be done at the time that it receives the data. Another example is looking at orders as they happen so that you can have an up-to-date inventory, so you can track the inventory in real time or near real time and do trend analysis. Another common example is looking at tweets. What's happening in tweets? Is there a fire going on somewhere? Is there some sort of virus that's going around in a certain part of the world, right? So doing that kind of analysis requires you to process the data as it comes in and analyze it. Okay, so the Spark Streaming works by dividing the data stream into micro batches of data, right? So this is the input stream. Spark Streaming will divide it into little micro batches of data, and then so each micro batch then will be processed by the Spark engine, right? By the transformations and the actions that you specify, and the Spark engine will process those operations. And Spark Streaming uses a high-level abstraction referred to as DStream, which stands for discretized stream. And this is implemented as a sequence of RUDs, right? Again, so everything is composed of RUDs. So any Spark operation can be applied to these D streams. Okay, so here's kind of a illustration of how that works. So this is a streaming source. You get the streaming data. Spark Streaming will discretize that into D streams. And again, underneath, they're made up of RDDs. And there are parameters that you can specify. So there's batch length. There's a window size, how big the micro batches are, and then the sliding interval. Right, and again, on the D streams, you can apply transformations and actions as normal. Okay, another library that comes with Spark is GraphX. So this provides distributed graph processing. So it has implementation for special structures for storing information about vertices and edges. And then also it provides operations for manipulating data in a graph. And the library, the RDD-based library is called GraphX, and the data frame-based library is called GraphFrames. And this again has APIs in many different languages, namely Scala, Java, and Python. So graph analytics is analyzing relationships among entities. So for a lot of applications, data is best represented as a graph instead of in a tabular format. So a common example is analyzing social media data, right, like tweets. So you have edges that represent nodes that represent entities, and then edges represent relationships between these entities. So when you analyze this sort of data, you want to, for an example of analyzing tweets, you want to look at, conversation threads, who's friends with whom, who's interacting with whom, where are the subgroups, who are the influencers of the community, who's retweeting what, that kind of stuff. So that is, those kinds of operations you can use graph analytics operations to analyze. So GraphX and GraphFrames provide these common operators and algorithms for graph analytics. And then finally, we also have a machine learning library, right? And that's referred to as MLlib. So this is a machine learning library that has distributed implementations of common machine learning algorithms and utilities. And Spark MLlib has APIs Java, Scala, Python, and R. And so Spark MLlib provides machine learning for classification, regression, cluster analysis, also evaluation metrics like F1, accuracy, precision, recall. It also provides statistics operations like summary statistics like mean, average, min, and max. Standard deviation, variance, and things like that. Also sampling. It also provides utilities for data processing that are common for machine learning and data science applications like dimensionality reduction, one-hot encoding, and other transformations. You can also create pipelines. If you're familiar with pipelines with scikit-learn, you can also do the same thing with Spark MLlib. All right, so here's some examples. This is some examples showing the statistics operations that are provided in MLlib. So this is generating a data frame with 2 columns of randomly generated numbers for different seeds. And you can do things like, show summary statistics, and you can apply statistical operations like finding the correlation between these two different columns. 2 different sets of randomly generated numbers. Okay, and then this is an example showing a cluster analysis using MLlib. So this is reading in a CSV file, and then this is performing k-means analysis, where you set the number of clusters to 3, and then you also set the seed. And this is fitting the data. So the syntax is, kind of very similar to scikit-learn. And then you can also print out the cluster centers after you have built up your k-means model. And we'll do one of our hands-on is a k-means model for clustering. So we'll see that more later. Okay. All right, and then, so one thing to note is that if you go to the Spark website, you'll see that there are 2 machine learning libraries. One is ML and the other is MLlib. So remember when Spark first came out, everything was RGD based, right? So they called that MLlib. But then when data frame became kind of the standard for programming, they created another machine learning library, and that's referred to as ML. But now the RDD-based library is now just in maintenance mode. And so when people talk about MLlib, they usually mean the data frame based. But you'll see that this still is around because there's a lot of documentation that exists here that was not carried over to the data frame based machine learning library. Okay, so the Spark libraries use the Spark engine as a core, right? So they are all built on top of the Spark engine. So they extend the functionality of Spark to different types of applications, right? So for machine learning, you use Spark MLlib. And there's also a website that provides third-party packages, right? So you can go there and take a look at other packages that are provided by other parties as well. So the idea behind Spark is it provides a unified engine for large-scale data analytics. It provides support for different types of workloads, and through all the things that we talked about, it achieves the goals of providing speed in processing, ease of use, generality, and a unified platform. Okay, and then there are some resources here. This PDF here is available in the repo. The PDF for the slides here is also available in the repo, and there are some other links here as well. Okay, any questions? Are we good? Okay. Yeah, questions?
Yeah, I have one question, Mike.
Yeah.
Mike, how is Spark different from a Dask?
Yeah, so they're both for scalable processing. Spark, Dask is a Python library, right? So it works only in the Python ecosystem. So, you know, it's the extension of Python. Spark is kind of its own ecosystem, right? So it does not only machine learning, but it also provides, you know, SQL and graph processing and things like that. And it has its, you know, it has its own, it's its own ecosystem, whereas Dask is just extension of Python. So it depends on, you know, what you're working with, right? So if you're strictly Python, you can check out Dask. But if you if you're working with, you know, things that are more general, and there are chances that you could have to incorporate Java code or R code, you want to look at Spark.
Okay. Is there any difference in performance as well?
So I think that depends a lot on the application. It's, you know, there's not a straightforward answer to say, yes, you know, Spark is faster or Dask is faster. It just kind of depends on the application. And with both of these, right, if you're familiar with scikit-learn, Dask will extend some operations, but not everything in scikit-learn. And similarly with Spark, right? So the MLlib library, you'll have, you know, lots of support for the commonly used algorithms, but obviously not everything that you can find in scikit-learn, or definitely not everything that you can find in R.
Okay, thank you.
Yeah, thanks for the question. Okay, any more questions? So why don't we take a little break until 1:45, because I'm gonna need a little time to get things set up for the hands-on. So let's break until 1:45 while I set things up. Jupyter Lab, right?
Yes.
And this, okay, fantastic. All right, so let's get started. Let's get all of this for now. Okay. Okay, so it's 1:46. So let's get started. So let's do some hands-on. We're gonna do short scaling and then cluster analysis. So you should log into Expanse. Right, so open a terminal window on your local machine and then SSH into Expanse like you've done before, using your account, XDTR something. Mine is XDDR, so some number that follows it. Okay, and then do a git pull when you're there. And let me know, let's see, I'll pull up the participants. Let me know when you are there. Give me a thumbs up if you are all following along. Or check mark or something. Right, let me, hold on here, okay. Okay, so do a git pull. And in the terminal window, type in Jupyter shared Spark. Right, this is an alias for this very, very long command here. So we are getting something from, we're getting resources from a shared partition, getting 4 cores, 16 gigs of memory for 4 hours. Then we're using this PySpark container, using Singularity Pro, and binding all of these directories. Okay. All right. Is anybody following along? Is anybody doing this? Give me Yes, the thumbs up or a check mark when you are at this point. When you've typed in Jupyter Shared Spark, you should get a URL. You can copy and paste that URL into your browser. And what you'll see when you have gotten your resources, you'll get Jupyter Lab and you'll see this here. This looks like this. Okay.
Is there a way we can copy paste, like typing will be?
Oh, you just, okay, then I guess I can put in breakout room. Okay, so it's just Jupyter Shared Spark. That's a command alias, so that's all you need to put in.
Okay, sure. Thank you.
Mm-hmm. Okay. Does everybody have Jupyter Lab up and running? Okay. Only one person? 2 people? Okay. All right. I'm going to move on. All right. So in the terminal window in Jupyter Lab, so you can go File. You can either click on the terminal here, or you can go File, New, Terminal. Okay. And by the way, this PDF here is available in the repo, so you can actually download it as well. But I'll also put this in the okay. So in the terminal window, you want to go to your local scratch, right? So this is okay. What is the git pull? So you just do git pull when you're in the terminal window and go into so if you have cloned the repo, you go into that repo locally, or not locally, sorry, in your when you log into terminal and do a git pull so that you can get all the latest stuff, all the latest changes to the repo. Does that answer your question, Gemma?
Sorry, I don't think I'm doing it right. I'm not sure where to type git pull or where to get
okay.
the repo.
So have you cloned the repo?
Which one?
The SDSC repo, the one that you've been using this week.
Oh, yes, I have.
Okay, so
Well, I think I have.
On Expanse?
Yeah.
Okay, so then you cd into that directory, so it would be called something like SDSC Summer Institute 2022. If you go into there in your Expanse account and then do a git pull, it should get all the latest changes.
I'm still not sure where to find that.
Okay, so in your terminal window, let me see. So how are you logged into Expanse? You have a terminal window, right?
Yes.
And you're logged in using your XDTR?
Well, I used the
account?
key that I set up with Marty, so I just did SSH Expanse.
Okay, so when you're there, can you do a git pull there and see what happens?
It says fatal, not a Git repository.
Okay, so you have to cd into, do an LS, do an LS like this. Do you see something that looks like this, SDSC Summer Institute 2022?
Oh no, I think I cleared it out. There was a point where I think I was following someone remove something and maybe I accidentally deleted it.
Okay, so you need to
maybe I need to get it again.
Clone it again. Yeah, so git clone. Yeah, there we go. Thanks, Marty. Yeah, so that should get all the latest stuff. And for those of you who already have cloned it, just CD into CD, I think it should be called this. And then git clone. Sorry, git pull. Okay. Okay, so right, so in the terminal window in Jupyter Lab, you do a CD. You're changing into your local scratch, right? So this is the local scratch. So this is the fast storage on the node that you are on, that you just got. So we're going to copy data to your local scratch, right? So if you do pwd, you should see something like this. Okay. All right. Okay, good, Gemma, thanks. Okay, so what we're going to do is then we're going to copy, and I'll put this in the chat as well. Okay, so you copy. Yes, and don't forget the period at the end, right? So you're copying this file called bookreviews.txt.zip to your scratch directory, your local scratch, and then you unzip it. Okay, then you do the same thing on this other file, which we're going to be using for the cluster analysis. So it's minute. Init weather.csv.zip, and then unzip that as well. Okay. And then once you've done that and you do an ls, you should see book reviews _5m.txt and then minute weather.csv. So this book reviews is Amazon Book Reviews. It has 5 million rows of data, so it's a subset of the very large Amazon Book Review data set. And we're going to just do some really simple processing on that data set. Okay, is everybody here? Can you give me a thumbs up if you are here? Awesome. Cool. All right. I'm gonna move on unless somebody has questions. Okay. So we're going to do a scaling hands-on. So again, we're using this data set, right? The book reviews data set. This is the original source for it. We are going to be using the PySpark demo. So if you are in your home directory here, you should have, SESC. This is your the repo, the local repo. So click into that, and then click into 4.3 scalable ML. And then Spark. And then you should see a PySpark demo. Okay, so open that up. Okay, so this is a very, very simple program just to show you how to run things, how to run a Spark program. So this is just importing some modules. This is initializing Spark. This is, remember, this is the creating the Spark session that we talked about. So this is the config object. So I'll talk about that in a minute. So this is a name, right? So this is the application name is Spark Demo. This is the amount of memory we want to use for the driver. This is the maximum result that we want to use for the driver. And then this is the executor memory. This here specifies that we are running Spark in local mode, right? That means we're not running on a distributed system. We're just running it on a single node. And this is specifying the number of cores. So here, we are just using one core. And what we're going to do is we're going to read this data set that we just copied over. And we are going to count the number of rows and show the first few rows. I think by default, it shows the first 20 rows. We are going to calculate the time that it takes to do these operations, right? To read it in. So the start time starts here, the amount of time that it takes to read it in, count the number of rows, and display the first few rows. Okay, and then at the end, we're going to stop the Spark session. Okay, so let's run this with a single core. Right, so let's do run all cells. Okay, and we'll see how long it takes with a single core. So the default parallelism, since we're only using one core, there is no parallelism, right? This is a scalar operation. So that is taking about 9.5 seconds, right? All right, so now what if we use 2 cores? So change this to 2, and then we want to restart the kernel and run all the cells so that it clears all the cache and starts it up again with 2 cores, okay? So restart that. Now we're running with 2 cores. So we should see some, that it processes things a little bit faster. Okay, so it's doing all this. And so we went from, was it 9.5 to 6.5, right? Using 2 cores. Right, so let's try and change it to 4 cores. Again, we need to restart kernel and run all cells. Right? And let's see how much faster that is. So we went from 9.5 to 6.5 to now we get 5.4 using 4 cores. Okay, so we see that there's some speed up, right? It's not, you know, a double. When you double the number of cores, it's not going to double because of, you know, communication overhead and all the things that Bob and others have talked about this week. So that this is what we have just been doing. So we changed this to a number of cores, and if you put in an asterisk there, that means use all available cores. So let's try to do that. So when we executed that Galileo command, we requested 4 cores. So when we put an asterisk here, it should use all cores, which means that it should use all 4 cores, right? So let's change that and restart the kernel and run all cells and see if we are using all 4 cores. Yeah, so we are using all 4 cores here. And was it 5 point something? Yeah, so it's about 5, I think it was 5.4 before, now it's like 5.5. So every time you run it, it's going to be a little bit different depending on the load, right? But so that kind of gives you an idea of you know, the kind of speed up that you can get when you run on multiple cores. Okay, questions on that? Did everybody get to follow along? Any questions? Okay, good, great. All right. Okay, yes.
Gemma is still having some trouble getting on. She's got, I think,
I have an error that my Scratch directory does not
Right.
exist. Okay, so you are in the terminal in the Jupyter Lab, right? Okay, so what you want to do is, let me put that in again in the chat. Yeah, what is your username, Gemma? Okay. So if you execute that command, that cd command, it gives you an error then? You can just do scratch, cd scratch, and then user, and do an ls and see what you see there. So just do cd scratch user. What does that give you? And then do an ls. Okay, so what does that mean, Marty?
I had that issue and I had to use the XDTR instead of $user.
Oh, okay.
Sorry, I was trying to find my mute. Yeah, can you echo your username there? And you're working from the Gemma, are you working from the portal by chance? Or are you working directly from SSH terminal?
Well, I have the portal open, but I was trying the commands in the terminal.
Okay. Let me see if I can get to it from your account real quick.
It looks like something is funny with this account. I'm gonna go on and hopefully we can get an answer from Marty for you, Gemma. Okay, so right, so this is the Spark program structure, Spark session. So here's some common commands here. Load data. If you load a CSV, you can specify whether that has column headers or not. You can also ask Spark to infer the schema. That means automatically determine the data types of the columns. Spark can do this, but note that this will incur some overhead, right? Because it has to ingest some data to figure out the data types. And then you can also cache the data. If you already know the schema, you can also specify that as well. And we'll see that in the next example. Here's some example for dropping nulls, checking the counts, checking the counts. Okay, so one thing to note is for Spark, which is different from scikit-learn or from R, is that you have to create a feature vector column in order to input data into a machine learning model in Spark. So this combines the list of columns into a single vector, right? This column has a single vector, and you need that in order to feed data into machine learning models. So for example, if you have two features, air temperature and relative humidity, that you want to use as input features, you need to assemble those into a single vector using a vector assembler, right? So the input columns will be these two features, and then the output column will be named feature vector. And so you create an assembler, and then you apply that assembler to your data frame, and this is what you're going to get. So this is your original data frame. When you apply the vector assembler to it, you'll get this additional vector at the end, and this is what's going to be used as input to your machine learning model. Okay. Okay, so I think it sounds like, okay, good. So I think we have a solution for Gemma. Okay, so this is partitioning data. Remember when, you know, with machine learning, building a machine learning model, you need to split the data into train and test data. So you can do this. This is a random split. And a lot of algorithms, you want to scale the data. So for example, in k-means clustering, we're going to be scaling the data. So you can use a standard scaler. This is very similar to scikit-learn if you're familiar with scikit-learn. So you input the unscaled features, and then the output column will be, you can specify the name of the output column, and then you can specify whether you want to divide by the standard deviation and subtract by the mean. Okay. And the important thing to remember, again, this is, you know, for all machine learning tools, is that when you do scaling, you want to use the training data for scaling and then apply that model to the training, the test, right? So you don't want to use any part of the test data to do the scaling. So this is building the decision tree classifier. This is the input column. This is the feature vector that we got from the vector assembler. And then you can pass in the ground truth, the label, and then the prediction column, you can specify the name for it. And then you fit that model to the training data. And then once you have the trained model, you can apply the model using transform to test data. And then there are different classes to calculate the evaluation metrics. So for classification, you can use a multi-class classification evaluator. And this will calculate things like F1, precision, recall, and accuracy. And this is the syntax to use that. Okay, so we just have a few minutes here. So I'm gonna, the next hands-on we're gonna do is a cluster analysis hands-on. The data is weather measurements, weather variables from weather stations. The task is to perform a cluster analysis to identify different weather patterns. And we're going to be using k-means from the Spark MLlib library. And oh, this is the incorrect location there, sorry. I'm going to show you where that is. So if you're in, it's in the 4.3b scalable machine learning under Spark, and you should see 3 different clustering, PySpark clustering notebooks. This is the starter notebook clustering. This is the starter notebook with output. So, you know, you can see what the output should look like. And then this is the solution notebook. Okay, so the data set is contains of weather measurements from a weather station on in Mount Woodson here in San Diego. It has weather measurements like, you know, air temperature, humidity, wind speed, and wind direction, and things like that. It has 3 years worth of data, measurements captured every minute, and the source of that is HPREN, which is a network of weather stations that was built and maintained here at SDSC. And this is the map of all of the HPREN weather stations, and this is the one that we're going to be using, Mount Woodson. Okay, so real quickly, cluster analysis. Again, the goal is to divide data into groups, and you want the similarities between points in a cluster to be as small as possible, and you want the clusters to be far apart as possible, right? So you want very distinct clusters. So k-means clustering, let's see. So here's a kind of the pseudocode for that. So you select k initial centroids, and you assign each sample to the closest centroid, and you calculate the mean of the cluster based on all of the samples that have been assigned to that cluster in order to determine the new centroid, and you repeat these 2 steps until some stopping criterion is reached. Right, so here's an illustration of what that looks like. So you have your you know, original data set, You find initial centroids randomly. You assign samples to the closest centroid. So all of these blue samples are closer to the blue X than to the red X, right? And once you have assigned all the samples, then you recalculate the mean for that cluster, and then you reassign the samples again, right? And then you repeat these two steps until some stopping criterion is reached. Choosing the number of clusters, there's different ways. An easy, commonly used approach is referred to as the elbow method. So the way that works is you compute an evaluation metric. In this case, we're going to be using WSSE, which is the within sum of squared error, for different levels of, for different values of K, for different numbers of clusters. And what you will see is that you'll get this curve that will decrease a lot at the beginning, and then at the end, it kind of levels off, right? So this is what's referred to as the elbow curve. So essentially what that means is that as you increase the number of clusters, you're getting diminishing return, right? So you want the point where it starts to, this curve starts to level off, right? So you want the elbow, you want to find the elbow. And that suggests the value or values for K that you want to try. This is the definition for the within sum of squared error. So it's just, let's see, taking each sample, the distance between that sample and the cluster center that it was assigned to, take the Euclidean distance of that, sum that up for all samples within that cluster, and then sum that all up across all clusters. So that's the within cluster sum of squared error. And this is just one metric to evaluate the clustering result. Okay, so here's what we're gonna do. We're gonna set it up, start the Spark session, load some modules, load the data. The minute weather data is what we're gonna be using. We're gonna do some EDA, right? Some exploration of the data. We're gonna prepare the data. We're gonna perform K-means clustering, evaluate the clusters, and then stop the Spark session. Okay, so I know that's a mouthful. I'm going to try and go over this. So I think given the time, I think I'm just going to go through the solution notebook just to kind of show you how it all works, right? I'm going to clear all outputs. Okay. Right, so we're going to start the Spark session here. Import modules. Let me make this a little bit bigger. Okay, read in the data. So this data comes from HPREN. And since we already know the data, right, we know the data types, we can specify the data type here. So these are, this is the timestamp. Most of these are doubles. All of the rest are doubles, right? So this is how we specify the data types for our data. And then we are going to read the data. So this is figuring out where the data is and then reading it in, right? So this is where our data resides. We do have column headers, and we're giving the schema that we defined up here, okay? So we're going to do some EDA, so exploratory data analysis. We're going to print the schema. Right, so this is a timestamp. These are all doubles down here. We're going to count the rows. This data set, we have, I think, 1.5 million rows. Yeah, so 1.6 million rows. Show summary statistics. So, GF describe is the main method, but it's a little bit, the output is a little bit hard to read, right? So you can actually convert that to pandas and then do some reformatting to make it easier to read, right? So that's all this does. So you have the number of rows, you have mean, min, and max and standard deviation for each one of the columns, okay? And then we're going to do some data preparation. We're going to drop nulls. right? So let's see, were there any nulls that were dropped? There were a few, right? So we went from 1.587 down to 1.586. So there were a couple of nulls that we dropped. And then we're going to create this feature vector. So remember, this is a feature vector that combines all of the input features into a single vector using the vector assembler. So that's what we're going to use, we're going to do here. And I'm going to show that. So this is what it looks like, right? So it kind of assembles all of these features into a single vector, and that's what gets fed into the machine learning model. For k-means, you want to scale the data so that, you know, no single feature will dominate the results. So this is using the standard scaler. We're inputting the features that we get from here. And then we are going to subtract the mean and divide by the standard deviation, right? So this is standardization or zero normalization, right? And then we're going to take a look at that. So now these are in a different scale now, okay? All right, now we're going to perform cluster analysis. So this is going to generate the elbow plot. I'm going to let it run because it might take a while. So this is, again, evaluating, calculating the WSSE for different values of K, which is a number of clusters. And as you'll see, with real data, it's rare that you will get a very nice, clean elbow, but you know, it'll give you kind of a range of values for K that you can use. Okay, so we're doing this from 5 to 14. So it's going to give you, so you know, this is the elbow plot, and this is kind of where it kind of starts to level off. So we're going to use K equals 11. So we're using 11 clusters for K means. We're going to with the scale data. So we're using 11 clusters. We're building the cluster model. And then when we're done with that, we're going to show the cluster centers and look at the cluster sizes. Hopefully this will. Okay, here we go. All right, so cluster centers and cluster sizes. So you see that the cluster sizes are different sizes, right? So there's one that has 120,000 samples and then one that has 75,000 around. Okay, so so we can do some analysis and use visualization to kind of analyze the kind of clusters that we're getting, right? So we can generate these cluster profile plots using parallel plots. So I think I have a picture here. So this is parallel plots. So what you're doing is you're plotting each cluster center, all of the dimensions in each cluster center, right? So there's air pressure for this red cluster, air temperature for this red cluster is here, and so on. And so remember that we scale the data, right? We standardize the data. So essentially, when we're looking at these values, you're essentially looking at the number of standard deviations away from the mean, right? So that means that this cluster has very high average wind speed and a very high max wind speed compared to the mean of all the samples, right? So this is essentially what this the cluster, the parallel plots show you. Okay, so we're gonna go through here, and this is looking at all the clusters, right? If we wanted to look at dry days, then we would look at relative humidity that is less than the average, right? The average is 0, right? Because that's we're looking at number of standard deviations away from the mean. So 0 would be average. Now we're looking at something that is below average. So these clusters 0, 6, 7, 8, and 9 are clusters that capture dry days, right? Weather patterns with below average humidity. On the other hand, these clusters capture weather patterns with above average humidity, right? And then these are clusters that capture hot days because the air temperature is greater than 0. And these capture windy days, right? Average wind speed, max wind speed are much higher than the 0. Okay, and then we can also save the model. And then at the very end, we want to stop the Spark session. Okay, so this kind of gives you an idea of how you can use Spark MLlib to analyze, to perform cluster analysis. Let's see what else I have here. Yeah, so if you wanted to do this on your own, you can start with the PySpark clustering or PySpark with output, clustering with output. And then wherever there's a, your code here, you can try to input your code there and see if you get it right. And then if you get stuck, you can look at this notebook, which is a solution notebook. This utils.py here has all the utility functions. Some resources here, the Spark website, Spark documentation, and also there's a Python for data science cheat sheet. This is a PDF that I also put in the repo for you. Okay, so real quickly, I want to talk about a couple of things. So as of Spark version 3.2, we're not using 3.2 here, we're using 3.1.2. Spark also has Pandas, Pandas API. So that means that, most of the commands that you're using, most of the Pandas command that you're using for your scikit-learn or for your Python code can also run on Spark, right? So the same code that can run with Pandas on a single node and on Spark on a distributed system. So it currently covers 83% of all the Pandas operations, and they are, of course, wanting to increase this number. So it's very simple to use. So instead of using, from pandas import read CSV, you say from PySpark.pandas import read CSV, and everything else should be the same, right? So I have not checked this out extensively, but it sounds like it would be very useful. Okay, so real quickly, R on Spark. Spark R is the R package. So it's, kind of the equivalent of PySpark. As you can use Spark MLlib. If you're familiar with Spark, it uses the same syntax as Spark, right? So this assignment operation you can use. And the cool thing is that you can run Spark R code on Jupyter Lab and on RStudio, right? So if you're an R user and you're familiar with RStudio, you can use RStudio and still connect to the Spark engine and run the code on a distributed system. There's also Sparkly R, which is also an R interface to Spark. It's not made by the Spark people. It's actually made by RStudio, the people that made RStudio. And so it has, the backend that uses dplyr. If you're familiar with R, you know that this is a very powerful package for data manipulation. And so this is just another package that allows you to access Spark functionality using R. And here's some examples. And then these are some machine learning algorithms that are available in Spark R and some resources. Okay, so these are the topics that we covered. I know it was a little bit rushed at the end, but all of this material is available in the repo, so feel free to take a look at it and try this out on your own because you have the starter notebook to work with. Okay, so I'm going to stop sharing here. We have a few minutes for Q&A. Let's see, any questions? I think there's a lot of. Yeah, I know it's a little bit hard with all these different things, right? You have the Zoom, you have the Slack, you have everything. So, but all of the material is available in the repo. So, afterwards, if you want to go back and take a look at this material at a slower pace, it's all there for you. Oh, good. All right. Fantastic.